In this video, we'll go over the answer key and our last answer key for Wednesday, April 29th. And what we're looking at here is electrolysis. Now, electrolysis is using an external source to run a reaction that's non-spontaneous. And it's carried out in what we call an electrolytic cell. So we were talking about galvanic cells, which is a spontaneous reaction. So the opposite of that is electrolytic cell, which uses a battery or another external source to drive a non-spontaneous reaction. You can also use electrolysis to separate elements. So here we have water. We're applying an external source to that water, and we're splitting up the elements to oxygen and gas. So our first problem is just to decide how an electrolytic cell is set up using nickel and cadmium. So the first thing you need to do is find the reduction potentials of nickel and cadmium, and then you need to combine them in such a way that your reaction would be non-spontaneous for your E cell. Remember, non-spontaneous for E cell means negative. And we want the non-spontaneous reaction because we're going to use a battery to drive that reaction forward or actually use that reaction. So here at the anode we have nickel, and at the cathode we had cadmium based on this equation. So our nickel is being oxidized and our cadmium is being reduced. So if you were actually to run this reaction, after a while you would see your nickel electrode would decrease in mass. It looks like it would be eaten away, while the cadmium would grow in mass. Looks like it is growing new material. Now, since we wrote down our half reactions, the direction of electron flow is relatively easy. Nickel is losing electrons, so electrons are going up, and cadmium's gaining electrons, so electrons are going down. And for the termini on the battery, whatever way the electrons are flowing, it flows to the positive termini, and they're leaving the negative termini. And the way to remember this is that opposites attract. So electrons want to go to the positive, and if you're the same charge, you repel, so the electrons want to leave the negative termini. Now, if you do electrolysis of pure compounds, such as a molten salt, you'll get a reaction which creates that compound, or it will convert that compound to what is normally found in nature for that pure compound. What I mean by that is, if we look at salt that's in the liquid form and we perform electrolysis on it, chlorine, which is a halogen, will go to chlorine gas, which is its natural lowest energy state. Sodium will go to sodium solid, which is its lowest state as a pure element or compound. Any anions will always be oxidized. Any cations will always be reduced. And you can see that in this reaction we want our electrons to match up. So we have 2 electrons on the left, so we also have 2 electrons on the right. That's why we have 2 sodium plus go to 2 sodium solid. So here's a reaction in which we are asking what will happen in an electrolytic cell. So we have an electrolytic cell that's made out of liquid potassium bromide. That's what molten means. It means the salt's been melted to a liquid. So potassium bromide and lithium bromide. So the first thing to do is write the half reactions that will happen when you split these elements up. Potassium will gain an electron and become potassium solid. Bromine will lose electrons, become Br2. Same thing for lithium, because lithium and potassium are in the same column. They all have the same reaction. Now we have to just realize which of these reactions will happen. The anion reaction is the same, so we don't need to worry about that. But the cation reaction, we have 2 choices. And so to do this, you look at your electron potential, or your reduction potential, and you want to choose the most positive element. Whatever is the most positive in an electrolytic cell will want to be reduced more. So potassium is a little more positive than lithium. So what we'll have is that we'll have our bromine go to Br2, and we'll have our potassium go to 2 potassium solid. Again, I have to multiply the potassium by 2 to match the number of electrons in my anode reaction. Now the last thing we're going to look at is stoichiometry. So when we're doing electrolysis, we have to be aware of the amount of electrons that are being transferred, and this will allow us to know how much product is being made. Basically, electrons are a reactant in this reaction. And we're going to use amps here. So when we are measuring power, one way to measure that is amp. And an amp is a coulomb of charge per second. And 1 mole of electrons is equal to 96,485 coulombs of charge. So 1 amp, if you want to think about this in terms of electrons, you would need 96,485 amps to move 1 mole of electrons per second. So that's a very high count, 96,000 amps. And this 1 mole to electron equals 96,485 coulombs of charge. That's actually Faraday's constant, which we have used before. So let's take a look at how we actually use this in a problem. So we are electroplating copper, and the half reaction is copper 2 plus 2 electrons goes to copper solid. And I want to know how much time it takes for 235 milligrams of copper to be plated if my electrical current is 5.6 amps. So this is just a giant unit conversion problem. So the first thing you want to do is you take your amps and you want to break that down to coulombs per second. So 5.6 amps is actually 5.6 coulombs per second. Using Faraday's constant, we know that 96,485 coulombs is 1 mole of electron. Alright, now our unit's in electron. We have canceled out coulombs. From our equation, we know that it takes 2 moles of electrons to interact with 1 mole of copper. Now our unit's mole of copper. And we know from molecular weight that 1 mole of copper is 63.55 grams. And let's convert that into milligrams. So 1 gram is 1,000 milligrams. So using copper at 5.6 amps, we know that we can plate 1.84 milligrams of copper for every 1 second. But I want to know 235 milligrams. So I'm just going to create a new conversion here. I want my time to be in seconds. So my second is going to be at the top. So every 1 second, I can plate 1.84 milligrams of copper. If I want to plate 235 milligrams of copper, that will take 127 seconds. So this problem is very confusing when you first look at it. But if you take it step by step, write down each unit. We have done these problems a ton in general chemistry. So hopefully, once you do look at the units, look at how this is set up, all that will come back to you and it won't be too bad of a headache. With that, that ends everything you need to know for Gen Chem 2, well, in the shortened virus-stricken age of 2020 spring Gen Chem 2. Good luck on the final, and let me know if you have any questions. I will see you sometime around, hopefully.